Namaskar. Welcome to Prakash on Basics. I am Prakash Zog. We've been talking of light. We'll move ahead a little bit. The world of colors makes everything around us look so beautiful. Being able to see different colors is what really color vision is about. The word chroma is used for color very often. And as I told you long back, it is believed that the human eye can distinguish between close to 10 million different aspects of color. But trying to understand the color theory could be a little confusing and difficult. So let us do that in very small bits. I may have to repeat a few things as we go along. I talked of some of the physics aspects behind how colors are produced a few months ago. The ability to distinguish or discriminate between different wavelengths that are there within the visible light is what really color vision is. When light falls on an object, its interaction with light determines what we feel as its color. It is what our eyes see, what our brain interprets. The mind processes the visual signals that have come. The data is interpreted and is compared with the information that is already stored in our memories, comparing them. Okay, this is that particular color, and that's how we interpret a particular color. Let's say white light falls on a tree. So the leaves will absorb all other colors and reflect only green. So that's the color that we see. On the bark, it's a combination of a few. Most of the other colors are absorbed, but something close to red and something close to the lower half is what is reflected back again, and that's the color we see. If it's a bright red flower that is around, then obviously it is red that gets reflected, all the other colors get absorbed, and we see that red wavelength, and we've been told that this particular type is known, this is what red is, like what you see behind, and the yellow that we see, and so forth. That's how we look at the shirt. So different colors that you see on this can be interpreted on the basis of what light is being reflected back towards you. So that's how we interpret colors. That's how we decide that this is a particular color. Actually, seeing colors has three different aspects associated with it. They are known as 3 P's: physics, physiology, and psychology. And the combination of these three is what is really talked of. Their combined effect gives us our perception of what color is. The wavelengths, their energies, their intensities, the image formation process on the retina, the nerve impulses that are produced, and their conduction to the brain, all that is a part of physics. I've already talked of some of it. The function of the eye, the retina, the rods, the cones, the optic nerve, the signal interpretation and its crossover when it reaches the brain, then the time delays that take place, the stereoscopic vision that we see, all that is associated with the physiological aspects. That is how our organs help us to interpret the information. And then depending upon the background, the adjacent colors appear slightly different. If the intensities are changed, they appear to be different. We perceive colors differently under different conditions. The same situation. Some colors we say they are said to be warm. That's because somebody tells us that these are warm colors. And then some colors are said to be cool. And every culture has its own norms of what is warm and what is cool and so forth. this attachment of emotions to color is the psychological aspect. So finally it is all three of them combined that decides on what color we see. But then let's go back a little bit. I told you that it is the cones on our retina that detect color. Photo is light, receptor is taking. So cones are the photoreceptors for color vision. And there is a small central area known as foeva, where the concentration of the cones is maximum. So whenever you have to test color vision or determine or study color vision, it is the level of light on the foeva that is usually studied, because the peripheral region has a little less cones, and so color vision is slightly less on the outer areas. So it is the central area that we must concentrate. One more thing I must remind you is that cones don't function below a certain threshold or a minimum level of intensity. Naturally, if the level of light is below that level, you are not going to see any colors. That's why in the dark we don't see any colors. We only see grey and shades of grey and black and white and so forth, and outlines, that's all. But then, as I told you, the human eye can detect so many different colors, and all that is because of the cones that we talked of. These cones have three different types of photoreceptors, type of proteins that are within them. They are known as opsines. So there are different opsines in three different types of photoreceptors that are there. Each has a peak response to a particular wavelength, and then it's like a curve. I'm going to just show it to you. And then there is a peak and it drops on the two sides. So there is one peak because of one type, second peak because of second type, third peak because of the third type. So color vision is because of these three different types, and depending upon when you apply physics, then the size of the wavelength could be either small or medium or large. So these are known as S, M and L type of cones, but then each one is associated with a particular color, and so small is close to blue, and the medium is close to green, and long is close to red. So they are identified as S, M and L type of cones, which respond to blue, green and red colors. Let's try and see how they appear. I have a graph for you. I hope it becomes clear enough as you see. I hope this is visible. I've tried to use different colors, and close to the blue color, which the blue peak that you can possibly see, this one is slightly lower than green, because our responses to green color is maximum. And I don't know if I have mentioned that sometime back, the temperature of the sun really decides on the outer surface, which is known as the corona of the sun. That is the one that decides on the type of light, maximum light that we get, and that is in the green region. And the rods that we have actually respond to this particular green region. As you can see, this blue peak is maximum, which is close to around 430 nanometers, and then it drops. As you can see, the curve drops down on this side, and by the time it comes here, it has no response. The green one has a peak that corresponds to 540 nanometers, and then it drops down, but it spreads outwards this side a little more. And actually the red one, which has a slightly lower response, is the one that spreads still further out. This is obviously the L type of cone, that is close to around 570 nanometers. That is actually very close to yellowish red, slightly beyond yellow and closer to the reddish area, and then it spreads out. Now what actually happens is, when light falls on any object, all three of them respond, but the amount of responses are different depending upon which type of color it is. So suppose I have a bluish green color, then obviously each of them will respond, and depending upon how the particular cone has responded will decide on the amount of impulse that it produces. Since there are three contributors, you can put this down in percentage. So let us say that green is around 70%, and 20% is red, and 10% is the blue cone that has responded. So the ratio is going to be 7:2:1 for these three peak. So naturally green is in the center, and so it is shift a little this side, and that is the area that is slightly beyond green, closer to the red area, and that's the type of color that you will see. And that's one of the aspects of how, in terms of percentages, a particular color can be identified. Things are not that simple. I'm going to come to that complex area maybe next time, not today. But right now, let's say this is good enough at this stage. That combined effect at the brain produces that particular sensation of the color that we tend to see. So every color can be identified in terms of percentage composition or in terms of ratios, and then maths and physics use graphs and charts and so forth. And if some of you all remember on your laptops etc., when you talk of colors, you get that graph, and when you select a particular color, the cross moves somewhere on that particular shade, and then you can decide on that particular color. So all that actually gives you the combination of the three of them. How many possible combinations? As I said, there are so many of them, and that is what gives us all those different colors that we tend to see. Actually, sometimes the same combination proportion can give us different, let me put it the other way around. I see one particular color, and that is obtained by a combination of R, G and B, red, green and blue, in the ratio of, now I am talking in terms of ratio numbers. As I remember, it is 86, 161 and 184. Now that gives me a particular color. Actually, if you look at of this combination, it is possible that I could have only green 161 and blue 185 and nothing of red, and still come very close to the same color. So one color can be obtained by a combination of 2 or 3 different methods, and that's what makes all these colors and their color schemes a little more complicated. Sometimes what happens is some of the cones don't function. Maybe S doesn't function, or M doesn't function, or L doesn't function. All the cones of that particular type either have low responses or don't function. It could be due to aging or some other factor, or it could be a genetic defect, and that is what gives rise to different types of color blindnesses. If the S type of cones are weak or missing, that means blue color is not very clearly visible, then you tend to see objects greenish red. If medium, that is the green color is type of cones are defective, then you tend to see things that are bluish and yellowish, but you don't see the intermediate colors that are around. It's a very rare possibility of all three cones being defective, and that really is total color blindness. Such people only see shades of black and white and grey, that's all, and that's no color response at all in the people. The effect of these responses depends upon the type of pigment that is there in all the three of them, and I'll talk of this in detail sometime later on, but it is our genes that decide, and it is the X chromosome that is the one that controls the existence of pigments that are there in the cones, and it is the X chromosome which may or may not have a particular type of a cone representation. Now look what happens in case of a female. Females have, if you remember from school, and I'll come to it later on, but just remember right now that females are X and X. Suppose one of the X's doesn't have S cone. It is possible that the other X chromosome will have that S. So finally that child will be able to see using the S pigment also. So there would be no problem. But suppose we talk of the males, their genetic composition is in terms of X and Y chromosome. So XY makes males. Now anyway the defect because of color is in X. So suppose X is defective and there is no M type of cone. Y anyway doesn't have anything to do with cones. So naturally this boy, because X doesn't have M, is without M in the cones. So naturally he is colorblind. So there is therefore a much higher possibility. The chances of both X's having the same type of defect is not really very common. So it is quite obvious that women do not have color blindness percentage as high as that in case of males. It is the males which tend to have this color defect to a greater extent. And surprising, but this is a very important thing that you must know. Some women have an extra color receptor. So instead of tri, that is 3, there are tetra. So their vision is said to be tetrachromatic vision. I don't have that. So I don't really know how these ladies would be interpreting using one more. Naturally you will see that many ladies tend to, no, this is not really matching. And this color is slightly different. Now we see it looks the same. Now it is very likely that such ladies might have a tetrachromatic vision. Some other animals also have that, but let's not go into that particular detail. Whenever we talk of colors and we try to understand them, there are some words that are used very often. We must know the meaning of these words also. Actually all colors are classified on the basis of 3 words and some other physics terminologies. One is hue, second is saturation of colors, and third is the extent of brightness of colors. The word hue is the different colors that are seen due to the cones. It is the dominant wavelength that is seen because of the combination of the 3 of them. And the earliest person, like I talked of last time in that color wheel, we know the 7 colors. So these are typically the 7 hues that are talked of. We have red, orange, yellow, green, cyan, blue and indigo. So these are in general the 7 of them, and there could be different combinations that will take place, but those are not hues. Now hues then are if one particular wavelength is very sharp and very clear and good, that single color identification because of a set of wavelengths is the hue of that particular color. Then there is another word, saturation. Sometimes the word tone is also associated with it, but there is a slight difference. The word saturation actually means the extent of purity of that particular color. Suppose I say that blue is around 430 nanometers. So if I have a whole bunch of only 430 nanometer light that falls on my eye, that is a saturated color, because all the other wavelengths have disappeared. The amount of purity of light is what is talked of in terms of saturation. But you can dilute it by 2 or 3 different methods. One is to add a little bit of white color to it. And when you start adding white, suppose I have red and I start adding a little bit of white, then what happens is the color becomes not red, but starts getting closer and closer to the pink shade that we know of, and lighter pink and so forth. I could do that to green, I could do that to blue, make it sky blue and still lighter and so forth. When you add white color to something and reduce the amount of saturation, that color, that type of color that you get is said to be the tint. So pink is a tint of red, and therefore we have so many different tints that are possible. It's possible that instead of adding white, you could add a little bit of black. And when you add a little bit of black, what you start getting is shades. So if I have red and I start adding black, I am going to start getting darker and darker shades of red moving either into black or lower down. If I do that in terms of green, I am going to get bottle green and lower colors and so forth. When you talk about ordinary blue and mix a little bit of black along with it, you start getting that navy blue color that we talk of. So that's shades. And there is a possibility that instead of adding white or black, you start adding grey, and that's the time that you usually tend to talk of it as tone. So you have 3 possibilities of making the original color a little bit impure, and that is how different combinations, depending upon the extent that is added, you start getting different amount of and different types of colors that we look around. The other term that I talked of is brightness or intensity of hue. Actually that's more associated with physics, because it is the amount of energy content per unit area per unit time that falls on a particular object. So when you say the light is very intense, there is more amount of light energy falling per unit area per unit time on the retina at that particular point. So it's more associated with physics, the brightness levels. And then it's possible that if we look at different objects, and it is this combination of the amount of brightness and the amount of hue and the amount of intensity that you have, that tells us what that particular color is. We've all seen ordinary light, and many of us have seen those light pointers. That, let's say I have a green laser pointer, that's green, and a very same green I see somewhere else, but the instant you see that pointer and the spot that is falling somewhere on the wall, you naturally realize that this is very bright. That is the actual hue, and it has a very high intensity. And if that intensity is reduced, then the color mellows down and so forth. These are just some of the terminologies. But what about the actual theory of what these 3 combinations are, and how did people really come about and do all this? We see so many colors, we see artists mixing colors, and then we have things known as pigments, and we have colors that are produced on TVs and our laptops and so forth. That deals with the actual theory of what color and color combinations are. That's the topic that we will talk of next time. That is equally interesting. If you liked whatever I have said, understand and try and interpret colors on your own when you look at them around you. Find out if they are brighter and see what happens when the background is around. Compare things as you go along. As I was talking, I thought of one more example which I missed out. Suppose you have, as I was talking, let's say white light falls on a red flower, and you see a red color. What it means is that red light has been reflected back, and the rest of the intensities and rest of the colors have been suppressed. Suppose I wear a red goggle and look at a red flower. Now it appears to be still brighter red. The reason is that small percentage of the amount of light that was getting reflected of other colors, that also is cut out by the glass. So the original flower now appears to be reflecting only red color, and that appears to be that much more brighter. So that's how bright colors, we see them slightly different than the ones in which there is a slight mixture. Right now behind you, you can see those two of them. The one here seems to be a little lighter than the one here. The reason is there is a slight percentage of white in that as it is being printed, and that makes a difference. So our color interpretations vary in this particular manner. If you have liked whatever I have said, please tell your friends about it. Do like and subscribe to this channel so that I will be able to communicate with you a little more, tell you a little more about so many beautiful things about color and lasers and so many other things. As I told you, we will be talking of a little more of this theory. It will get a little complex and a little complicated, but it's very interesting. Till we meet again next time. Namaskar.